to the pH scale. And the pH scale is based on the molar values of the hydrogen ion concentration in solution. So it measures the acid concentrations of solution. pH actually stands for parts hydrogen, and it ranges from 0, which is the most acidic, to 14, which is the most basic, to neutral. And water is H2O, so if you break it up, it's this, it can actually dissolve itself or break apart their own molecules of water, and so it can break apart itself. And it breaks down into hydrogen ions and hydroxide ions, which is negatively charged, and hydrogen is positively charged. That makes the water up. But in a neutral solution, like distilled water, you would have an equal number of hydrogen and hydroxyl. And it just so happens that that molar value is 1 times 10 to the negative 7th. So negative 7 is the power of 10, and the log is, just to simplify this, it's the power of 10 of a number. And so if the hydrogen ion concentration is 10 to the negative 7th, then the log is negative 7, and the negative of a negative 7 is a 7. So that would give distilled water a pH of 7. 0.1 molar would be 10 to the negative 1, and if you take a negative of negative 1, it's 1, so you'd have a pH of 1. So the higher the concentration of hydrogen ions, because 0.1 is much, much bigger of a value than 0.00000, like a 10 would be 0.0000000. The point is that the higher the concentration of hydrogen ions, the lower the pH. And the lower the concentration of hydrogen ions, the higher the pH. That's it. So, and if you were talking about like electrolytes, for example, that they're able to conduct electricity and such, acids are ones that release hydrogens into the solution. Bases are ones that release hydroxyls, or they take up hydrogens from solution, and so that there is an imbalance of hydrogens to hydroxides. And so the higher, again, the hydrogens, the lower the pH value. And that's just the neutral solution. They have an equal number. So to calculate the pH, let's do one example here. You would have this solution, 0.000000001 molar. That particular concentration, if you were to put that's the hydrogen ion concentration, and pH is the negative log of the hydrogen ion concentration. So if we were to write that concentration in scientific notation, it would be 1 times 10 to the negative 10th hydrogen ions. So the log of that number is negative 10, and negative of negative 10 is a positive 10. So the pH would be 10. And again, that's going to give you, that would be a base, because acids are 0 to 6.999, neutral is 7, and bases are 7.1 to 14. So again, the higher the concentration of hydrogen, the lower the pH value. Inorganic and organic compounds. This kind of transitions us. We're getting ready now to talk about organic compounds. But we need to know what they are first, and then we can talk about the big macromolecules that are organic. Inorganic molecules or chemicals do not contain hydrogen and carbon. So sodium chloride, NaCl, does not contain either carbon, nor does it contain hydrogen. So it's an inorganic molecule. CO2 it does contain carbon, and this is what confuses a lot of people, because they think organic means it's either natural, or because we use that term in talking about food, that organic is natural, or they think it's always carbon-based. Well, yes, it's carbon-based, but it also has to have hydrogen bonds in there. And if there's no hydrogen, then it can't have a carbon-hydrogen bond. So organic chemicals contain carbon and hydrogen, as well as other chemicals like sulfur and nitrogen and oxygen, and phosphorus. So those are some examples of organic molecules. And again, it has to contain both carbon and hydrogen. If it just contains carbon or if it just contains hydrogen, it's still inorganic. Most of the chemical reactions and structures of living things involve organic chemicals. So the importance of carbon is that it has a valence. That means that it has 4 electrons in the outer shell. And it can form a linear structure, branched or ringed. And so this is the various combinations you can have of these carbons, carbon being at the center, and then you have hydrogens and oxygens and nitrogen and phosphorus and sulfur all off of these branches and off of these lines and such. So most can form a single, double, or triple bond, and they often associate with hydrogen, oxygen, nitrogen, sulfur, and phosphorus. So this is the big reason why carbon is important, is because it has 4 electrons in its outer shell. And, you know, there's a lot of elements that have 4 electrons in their outer shell that are in that same family. But for whatever reason, carbon is just the one that combines well with all these other atoms. And it just works best. So the functional groups that you're going to need to know are listed here, shown here. And they're special molecular groups of organic compounds. And they give the compounds unique reactive properties because shape dictates function, and these particular functional groups give them their particular shape. So in lab, we'll get together and we'll put together some of these particular functional groups so you can see how they work. But everything, if they have a carbon double bonded to oxygen, that's called a carbonyl. And if it's connected to a hydroxyl here, then it's a carboxyl. So hydroxyl is OH group, and the hydroxide is the hydrogen ion. But if you see just an OH at the end of a molecule, then that's a hydroxyl functional group. And you find that in alcohols and carbohydrates. If you combine that hydroxyl, and I realize there's like a little piece missing right here in the picture, but there would be a bond between carbon and oxygen, and then double bonded between carbon and oxygen here. That would make this a carboxyl. So it's a carbonyl, C double bonded to O, and hydroxyls, it's OH. So if you combine those two together, you get carboxyl. And that's found in fatty acids, proteins, and organic acids. That's typical. Then if you have a carbonyl combined with an oxygen, and then there's a reaction group after it, it's not at the end like this one is at the end of the molecule because it's got the hydrogen there. But if instead of hydrogen you had a reaction group, that's called an ester. So if it's carbonyl with an oxygen and then the rest of the molecule, so COO would be how we talk about that, it's an ester. If it's COOH, that's a carboxyl. And then if you just have a carbonyl that's at the end of the molecule, not attached to an oxygen but attached to hydrogen, that's a terminal carbonyl, that's an aldehyde. And if you have a carbonyl that's in the middle of the molecule, so over here there's another carbon, and or there's a carbon over here, there's a carbon over there, and so it's in the middle of a molecule, that would be called a ketone group. So the carbonyl that's internal is a ketone, the carbonyl that's terminal, there's a hydrogen there instead of carbon, that's an aldehyde. And then if you have a carbonyl with an OH, that's a carboxyl, and a carbonyl with just an oxygen, that's an ester. So these 4 are the ones that I think you're going to have the most difficulty with. Amino is just NH2, and it's the only one that has nitrogen in it, really. Sulfahydryl is just sulfur and hydrogen, so that makes sense and not very difficult. Phosphate has phosphorus in it. So of all of these, the 4 that I think are going to give you the most difficulty would be the carboxyl, the ester, the aldehydes, and the ketones. So make sure you go over those. You'll have pictures of these on the test, or you'll have to draw them, or you'll have to circle the different functional groups and identify them in a molecule. So make sure you can do that for the functional groups. So what type of reaction is illustrated here? If you had 2H2 plus O2 and you got 2H2O. So think back to the different kinds of reactions. Is it decomposition, A, synthesis, B, exchange, C, or spontaneous, D? If you answered synthesis, then you would be correct, B.